Hi, everybody. Today's lesson is for Friday, April 3rd. I hope you're all doing great. Just wanted to say hello. Hopefully I'll see you in online office hours, but let's go ahead and get started with the lesson. All right, so intro and admin, you see I have exam 2 updates written down here. The truth of the matter is I'm recording this lesson on Monday, so exam 2 has not happened yet, but I will be hard at work grading it. I'm hoping to get it back to you guys as soon as possible. My guess is it'll take me through the weekend, so ideally Monday you guys will get some feedback from me about the exam. Please don't hesitate to reach out if you have any questions or wanted to discuss anything about the exam in particular. But I know this is sort of after the fact, but I hope it went really well for you guys. I guess past tense, good luck. And yeah, I hope it went great. In terms of today and sort of continuing on from lesson 28, which we talked about environmental loading last Friday, it was more of an introduction lesson. We had a PowerPoint, talked about the 100-year wind speed, wind variation with elevation, specifically mentioning also that we were going to focus on wind, current, and wave loading. So the plan for today is to do some examples, talk about how we actually calculate the wind force on a structure and what guidance API, the American Petroleum Institute, provides for calculating wave forces on structures. And we'll also introduce wave, mostly really just wave properties today, but that's going to segue into wave and current loading. Full disclosure, you guys could probably teach this lesson yourself on waves based on your expertise from EN 475. So what we're doing in here will probably be a bit of a review of that. Anyway, let's go ahead and get started. So again, last time we sort of started this new unit on environmental loading. So this is kind of continued. And again, Roman numerals 1 and 2 are intro, as well as sort of the introduction to wind loading. Those are going to be continued from lesson 28, see handout. But the takeaways really is that we're going to focus on wind, current, and waves for our kind of introduction. That was sort of a big takeaway from that. And then moving into wind loading, the big takeaway sort of from that part of the lesson last time was that wind speed determines the total load. And again, in that handout, we talked about some ways to estimate the 100-year wind speed, different annual recurrence probabilities, what to do sort of moving inland, offshore, how to account for gust factors, and things like that. Today, let's talk about once we have that wind speed, how we actually calculate the wind load on structures. And we calculate the wind load. This is actually going to be very similar to maybe some of the things that you've talked about in fluid dynamics. So to calculate the wind load, you'll use the fluid drag force equation for the fluid drag force on an object. So the fluid drag force on an object can be calculated. Here's the equation. Our drag force F sub D is equal to 1/2 times rho times U, our velocity squared, times a coefficient, times our projected area. And let's go ahead and define some terms. So if we want to maybe draw a definition sketch, let's say I have some wind coming this way, it'll be a uniform wind vertically with some speed u. And I might have some structure. Let's see how well I can draw in 3D. Answer is not very. But let's say our structure is here. Ground elevation. And here we have our area that is exposed to the wind. We call that the projected area. So again, if I define terms, F sub D is equal to my fluid drag force. Rho is my fluid density. Since we're going to be calculating wind forces, the most common fluid we'll have is air. So please note that the density of air in English units is 0.00238 slug per foot cubed. And U is the fluid velocity. Again, we'll probably be working in English units since we're doing a lot of API checks in feet per second. A sub P is equal to the projected area. So this will be in feet squared, or a unit of length squared. Note that this is the area perpendicular to the fluid flow. And then finally, C sub D is equal to our drag coefficient. Note that this is C sub S in API. This equation actually is given in the API standard. The equation number is 2.3.2-8 if you want to check out sort of that full standard for API's equation. This is going to be empirically determined. And there's been a lot of research on drag coefficients. We'll talk about that a little bit more in a second. But first, let's talk about the projected area. I'm gonna, shift down just a bit. And this will be number 2, our projected area. A sub P. Again, this is perpendicular to fluid flow. So what that means is, for example, let's say I have some pyramid-shaped structure with kind of a sloping side. And then maybe a flat top. And here's our ground coming here. And here's our wind speed. And let's say we have some dimensions. Let's just keep them in just variables for now. So let's say we have some width W. This is the area of the side that's exposed to the wind. Here's H, the height of this pyramid structure. And here is, let's just call this length, just to here. This is going to be, let's just call this L. And if I wanted to calculate the area, so if I wanted to find the actual area of this side, I need to take this side. So this is basically just a rectangle. So I need to find, using the Pythagorean theorem, the length of this side will be the square root of L squared plus H squared times my width. But if I take the projected area that's perpendicular to the flow, basically I could extend this out here. And I'm going to have some shape that is still a rectangle with height H and width W. So my projected area is equal to H times W. Cool. Let's do another example. So example 2, I'm going to slide down just a little bit more. So this will be letter B, example 2. If I have a cylinder with diameter D and length L, and we're on ground, and we have again some wind that's blowing with speed U. If I were to project this forward, again, I'm sorry about my poor 3D sketching. Basically, it's going to just look like a rectangle with height L and width equal to the diameter of the pile. So this will be my projected area, which is equal to D times L. And that's the face of the pile, or the portion of the pile that's getting exposed to the wind force. All right, let's keep talking about this drag force equation and talk a little bit about the drag coefficient, C sub D. And the first thing I wanted to note is that C sub D is a function of, so this means is a function of the object shape. So whether it's a cylinder, rectangle, etc., as well as the Reynolds number. And you guys have probably talked about the Reynolds number in your fluids class, but just as a bit of a refresher, the Reynolds number is equal to rho times the dynamic, times the velocity times some characteristic dimension, all divided by the dynamic viscosity. So this is our equation. Let's go ahead and define some terms. So again, the Reynolds number, R sub E, or RE is equal to Reynolds number, which is dimensionless. Rho is equal to our density. So in English units, we're talking about slugs per foot cubed or something similar. Capital U on top is our velocity of the fluid, so feet per second. D is our characteristic length, dimension. So that will be in units of feet or meters. And then finally, mu is our dynamic viscosity. And the units of this are pound times second divided by feet squared. And this is a really useful tool. Another way to think about this Reynolds number is if we think about sort of the density times the velocity times sort of the amount of how big this fluid column or fluid shape interaction is. That's kind of like the inertial force, or it is the inertial force, divided by viscosity is another way to represent friction in fluid flow. So we're basically comparing our inertial forces to our viscous or friction forces. And if the Reynolds number is really big, we can say that inertial forces dominate. This is the case for most engineering flows. So sort of as big letter 2 for most engineering flows, the Reynolds number is large, and we can ignore friction. But there's been a lot of research on how drag coefficients are affected by the Reynolds number. So for number 3, lots of research on drag coefficients. As a bit of an aside, a lot of the research that I do looks at mangroves or natural and nature-based features and how they can provide coastal protection, so how they can reduce forces on inland structures. Some other people who are studying mangroves have done some really cool experiments where basically they built some mini mangroves in a flume and actually installed load sensors on the mangroves so that they can actually calculate what the drag coefficient is on these mangroves. So that's a kind of cool application sort of research-wise. But I'm gonna go ahead and share my screen. So let's go share screen. And I'll share the handout that's posted in this folder or in this material, depending on if you're on Blackboard or Google Drive. There's a lot of other examples like this. So this figure 3.3 shows on the x-axis we have the Reynolds number, and on the y-axis we have that drag coefficient. So basically we're plotting C sub d versus the Reynolds number for either a long circular cylinder or a thin rectangular beam. So that's just one example. Again, there's many, many different representations of how the drag coefficient changes with the Reynolds number. If we scroll down, API also provides guidance for drag coefficient. So here you can see the recommended values for beams, cylinders, sides of buildings, and projected areas of offshore platforms, which are typically sort of open and graded. And we'll talk more about that when we get to our example. So I'll go ahead and stop my share. And we'll just get for the notes, we'll say C figure 3.3, which plots C sub d versus the Reynolds number for a thin beam and circular cylinder. And then also we have table 3.3, which is API recommended values of C sub d for buildings, beams, cylinders, and open platforms. All right, so let's talk about force calculations using API recommendations. So I'm going to slide this down just a little bit so that we can continue on. Great. And so we have force calculations. With API. Really just one important note or kind of distinction to make when you're calculating these forces. If you have a solid face, so like the side of a building or something, you're just going to use the equation as considered. So only consider the windward or the wind-facing face. So this is like the side of a building, etc. But again, the American Petroleum Institute deals a lot with offshore oil platforms. And so if you have something like a platform, you actually have to consider your projected area is equal to the sum of all 4 sides of the platform. And the reason that API does this is because you can have wind that passes through gratings or sort of through gaps in platforms, which typically have a lot of gratings to allow, you know, overwash to wash off, etc. So wind can pass through gratings and around columns. And so using the total sum of all four sides of the projected area is a conservative approach to calculating the projected area. All right, so let's go ahead and do a couple of examples. So for example, this will be example 1. We have an offshore platform with a deck house. And so what that looks like, again, we'll have some wind coming across the ocean. Let's say our wind speed is 150 miles per hour. Here's a sketch of the platform. It's maybe got some gratings here. And we've got some deck house where maybe you're storing machinery, equipment, people do work in there, etc. So here's our deck house. And here's our platform. And we know that for the platform, the area of the windward and leeward, so the sheltered sides, are equal to 700 feet squared each. And the area of the side faces are equal to 400 feet squared each. And for our deck house, similarly, we have different areas. So the area of the windward and leeward faces are equal to 200 feet squared each, so per face. And the area of the side faces are equal to 300 feet squared each. And we want to find the force due to the wind on both the deck house and the platform. So first, let's go ahead and calculate the force due to the wind on the platform. So we'll find for the platform. And again, our base equation is always going to be that the force, and this will be, let's just call it F plat, is equal to 1/2 times the density of air, rho, times our wind velocity squared, times our drag coefficient, times our projected area. Again, rho here is going to equal 0.00238 slugs per foot cubed. U is equal to 150 miles per hour. Be really careful with units here. To make this dimensionally consistent, we need U to be in feet per second. So I'm going to multiply this times 5,280 feet in 1 mile. And then also times 1 hour is 3,600 seconds. And so this will come out to be 220 feet per second. The projected area, since we have an open platform, we're going to sum all sides. And so this will equal 2 times 700 feet squared. So the windward plus the leeward sides, plus 2 times 400 feet squared for our side faces. And this is equal to 2,200 feet squared. The last variable I need here is my drag coefficient, C sub D. And if I go back, I'm going to share my screen again. And let's look at this drag coefficient table. So again, we can look at table 3.3, and we see that for the projected area of a platform, our drag coefficient recommendation is 1.0. And again, this is sort of a non-conservative value for using a drag coefficient because we're not increasing the value of the wind force. But the reason why you can use a factor of 1 is, again, because you're being so conservative with your projected area when you're considering offshore platform. So we have C sub D equals 1.0. Plugging all of these in, we have the platform wind load is equal to 1/2 times 0.00238 slug per foot cubed times 220 feet per second, that quantity squared, times our drag coefficient is 1, times 2,200 feet squared is our projected area. This comes out to be 126,711.2. And if you track your units here, basically you're going to end up with slug times feet per second squared, which is equal to a pound force. So therefore, I can say that the force on my platform is equal to 126.7 kips. For a platform, it's a little bit tricky. You don't really know the area, the location to apply this force. So you would be needed to get more information in the problem about where to apply the force, maybe at the front side of the platform, on top of one of the piles, or something like that. Let's go ahead and calculate the force on the deck house. So second, we'll calculate the force on the deck house. And this is equal to, again, 1/2 rho u squared C sub D times our projected area. Everything's the same for our density of air is not going to change. Our wind speed is the same. Now, if I look at my drag coefficient, let's go back and check out our API design tables. Again, we have the drag coefficient for the side of a building equal to 1.5. So I can just jot that right down for my drag coefficient for this deck house. And remember though, since we have the solid side of a building, sorry, I went and I pointed, but I realized I'm off the screen. Since I have a solid deck house, this means that the projected area is equal to the windward face area only. So my projected area here is going to equal 200 feet squared. Plugging all these numbers in, I get that the F of my deck house is equal to 1/2 times 0.00238 slug per foot cubed times the wind speed is 220 feet per second, that quantity squared, times 1.5 times 200 feet squared is equal to 17,278.8 pounds, or the force on my deck house is equal to 17.3 kips. And for something like a deck house, you can assume that this acts at the centroid of the windward face of the deck house. So apply at centroid of area. All right, hopefully that's making sense. Let's do one more example. What I would recommend is maybe pause the video here and try to work through this example on your own, and then we can come back together and I'll talk through the solution. So here's example 2. We have an offshore, cylindrical pile at an incline. So maybe it got bumped, maybe it's inclined by design, but at any rate, our pile is fixed into the ground. It's in a water depth. We know the total length is 70 feet with 35 feet exposed and 35 feet underwater. We know the diameter of the pile is equal to 2 feet. And we know that the wind speed only acts above the water, and it's equal to 150 miles per hour. And last, we know that this incline is equal to 60 degrees. So again, if I want to plug in to my drag force equation, I can use 1/2 rho u squared c sub d times my projected area. Here we have our density of air is going to be 0.00238 slug per foot cubed. Our drag coefficient, if I consult the API table for piles, they recommend using 0.5. So this is from table 3.3 in API. And my projected area is going to equal, this is where it gets a little bit tricky. Again, remember your projected area is the area of the rectangle that you project from this inclined member. So basically I want this y distance, which will be L exposed, so my exposed length of 35 feet times the sine of 60 degrees times the diameter of my pile. So it's equal to 35 feet sine of 60 degrees times 2 feet, which is equal to 60.6 feet squared. And then lastly, my wind velocity U is 150 miles per hour. Remember to convert that to feet per second. That's the same value we had from example 1, so we can go ahead and plug in 220 feet per second. Plugging all of these numbers in, I come up with a drag force on the pile equal to 1.745 kips. And when you have an inclined member like this is acting normal to the cylinder. So what that means is if this is my cylinder at an incline, my drag force is going to be acting perpendicular to that cylinder. And if I have, this angle is 60 degrees, that means I know that this angle is 30 degrees. So I can resolve this drag force into the X and Y components, where I might have FDX and FDY, with my drag force in the X direction equal to my total drag force times the cosine of 30 degrees, which is equal to 1.512 kips. And then similarly, my drag force resolved in the Y direction is going to be the drag force times the sine of 30 degrees, or 0.873 kips. And that's pretty much the extent of what we'll be talking about for wind loading on structures. So just make sure you're really familiar with this equation of F sub D, how to be careful with units, how to find those drag coefficients are sort of the big takeaways from these calculations. I'd like to push on, and again, if we run a little bit overtime today, I'll make it up to you guys with Monday's lesson. But I'd like to at least introduce kind of some wave and current definitions, which will be really similar to your waves class. So again, you guys are already pretty well experts at this. So this will be major topic 3. We're gonna start talking about wave and current loading. And let's do a lightning review of some of the concepts from EN 475, the waves class you guys are all in. So let's talk some definitions. And again, a really important simplification that we make when studying ocean waves is that these waves can be idealized. So idealize ocean waves as sines and cosines. And so if I draw maybe my still water level above some depth, when this is the bottom, and this is my depth D. And let's draw some waves over top. So we can draw these nice sine or cosine curves that represent our ocean waves. Again, the top of a wave is called the wave crest. The bottom of the wave is the wave trough. And let's go ahead and add some variables to this sketch as we define some terms. So first we have our water depth, which is D, which is essentially equal to the elevation of your still water level minus the elevation of the bottom. This is a unit of length, so we're thinking about feet or meters here. The next variable we have is eta. Eta is the free surface elevation at any given moment in any given place. So here we have eta, which is a function of x, my position, and time, t. So eta is equal to, again, my free surface elevation at a given position, so x, and time, t. The units of eta are going to also be in length, so feet or meters. And we have an equation for eta, again, simplifying this as a sine and cosine. We have eta is equal to 1/2, so h over 2, 1/2 times my wave height, times the cosine of k times x, my position, minus omega times t. So more on my wave number k and my frequency omega coming up. Again, h is equal to my wave height, which is the vertical distance from crest to trough. Again, this is in feet or meters. So if I were to draw this here, I would extend out from my crest and from my trough. And h is going to be that vertical distance. Remember that the amplitude then is equal to 1/2 times h. So the amplitude is just basically the distance from the still water level to the crest. The amplitude, this is equal to my amplitude. And let's talk about our wavelength, L. This is the wavelength, which is the horizontal distance between successive wave crests. Again, this is a length, so feet or meters. We can draw that on this chart where we have, I go between wave crest and wave crest. Here's my wavelength, L. Just as a general note, this isn't the standard, this isn't always the definition for wavelength. Sometimes you might see other definitions like zero up crossing. So you go from up crossing to up crossing. So other ways to define your wavelength exist, and sort of to differentiate between what a specific wave is. Importantly though, once you know L, you can calculate your wave number, K, which is equal to 2 pi over L. This is equal to your wave number. And the units of this are in radians per foot and radians per meters, depending on English or SI units. And then finally, the last term to define here is T, which is equal to our wave period, which is equal to the time between successive wave crests at a fixed location, X. The units of your wave period, of course, will be in seconds. And sort of similar to the wave number, we can define our wave frequency, omega, is equal to 2 pi divided by T, which is equal to our wave frequency. And the units of this will be in radians per second, or you might see 1 over seconds because sometimes radians is considered units. For idealized linear waves, which is what we'll be working with here, so linear wave theory for idealized linear, or you guys might call them airy waves. We can relate our wavelength to our period, or essentially we can relate our wave number to our wave frequency using the dispersion relationship, which tells us that omega squared is equal to G times K times the hyperbolic tangent of K times my water depth. If we're in shallow water, we have D is small or L is large. And what do I mean? How small, how large? Basically, we require L divided by D to be greater than 20. If this is the case, we can say that the hyperbolic tangent of K times D can be approximated as K times D. So plugging that in, our dispersion relationship can be simplified to omega squared is equal to G times K squared times D. On the other hand, if we're in deep water, so we have D is large or L is small. And again, how small, how large? Basically, we need L over D to be less than 2. Then we have the hyperbolic tangent of K times D goes to 1. And so we have omega squared is equal to G times K is how we can simplify our dispersion relationship. This boxed equation always works, so you don't ever need to plug in these equations, but it is a way to sometimes simplify your calculations. Last term to define before we do a quick example is wave celerity. So here we have wave celerity refers to the speed of the wave. And this is equal to the distance I travel, so the change in x, divided by how long it takes the wave to get there, so delta t. And the equation itself, so the wave celerity c, can be calculated as the wavelength divided by the period, or if we plug in 2 pi over k and 2 pi over omega for L and t respectively, we can calculate it as omega over k. And the units of this are a velocity or a speed. So this will be in feet per seconds or meters per seconds. Important to note that C is not the water particle velocity under the wave. This you have to calculate by taking the derivative essentially of your water surface elevation. Those are on your equation sheets from EN 475, and they're also posted in this online content material in Blackboard and Google Classrooms. So, all right, let's move on and do one quick example, and then we'll wrap up for today. So this will be number 4, our example. Find the wave period and wave celerity with a surface, or sorry, of a surface wave with a wavelength of 300 feet and in 60 feet water depth. All right, so that's our problem statement, not visible, sorry about that. Our example is to find the wave period and wave celerity of a surface wave that has a wavelength of 300 feet, and we know that it's propagating in 60 feet water depth. Whenever I solve these problems, for whatever reason, I really like to draw a sketch. This is totally optional, but it kind of just helps me to organize what information I have and what I need to find. So if I draw a quick sketch of my wave, here's my water surface elevation, which is supposed to be the same depth. I know my depth is equal to 60 feet, and I know that my wave has a wavelength of 300 feet. And I also know that gravity in English units is equal to 32.2 feet per second squared. Kind of all the information I have, but that's plenty to calculate what we need to calculate. So if we want to find our wave period, we just said that the dispersion relationship is how we can relate T to L. So the dispersion relationship tells us that omega squared is equal to G times K times a hyperbolic tangent of K times D. Typically when I'm doing waves problems, I almost always write down this equation first. It's usually a good place to start if I'm still trying to organize my thoughts. Knowing that, we can check if we can simplify. So we can say, note that L divided by D is equal to 300 feet divided by 60 feet, which is equal to 5. Unfortunately, it's greater than 2, so it's not in deep water. And it's less than 20, so it's not in shallow water. So therefore, we know it's in intermediate. And we need the full form of our equation. So we have to use omega squared is equal to GK hyperbolic tangent of K times D. Let's go ahead and plug in, since we're trying to find periods. So we can say 2 pi over T, this whole quantity squared, is equal to G times 2 pi over L times the hyperbolic tangent of 2 pi over L times D. And then I can rearrange and simplify a bit and solve this for T. So I have that my wave period is equal to the quantity 2 pi times L divided by moving all of this to over here. So we have G times the hyperbolic tangent of 2 pi times d over L. This quantity taken to the 1/2 power, so the square root. Plugging in numbers, we get 2 pi times 300 feet divided by 32.2 feet per second squared times the hyperbolic tangent of 2 pi times my depth is 60 feet divided by my wavelength of 300 feet to the 1/2 power. My hyperbolic tangent is unitless. That's good. We're going to get feet divided by feet per second squared. So eventually we're taking the square root of second squared. And we get that my wave period is equal to 8.3 seconds. Awesome. And then once we have our period, it's pretty quick to calculate wave celerity. We know that the wave celerity, C, is defined as the wavelength divided by the wave period. Now we know both of these numbers, so we have 300 feet divided by 8.3 seconds. So we get that C is equal to 36.1 feet per second. All right, guys, thanks so much for hanging in there with me. Next, we're going to talk about wave forces on piles. So once we have all of these information about the wave properties and the wave parameters, how can we actually calculate what the wave force is on the pile using Morrison's equation? So thanks so much. Have a great weekend, and looking forward to seeing you guys soon.